or to the cloud. Right.
You guys hear me okay over there?
Somebody give me a thumbs up, maybe. No?
Could you mute on one of your accounts? It's echoing.
Sorry, I can't hear you. If you're speaking to tell me it's okay. Can you mute one of the accounts? Yes.
How is that? Can you hear me now? All right, there we go. Better, thank you. Okay. Two machines. All right, that's challenging. Right, so so this is a great way to represent wave functions. As we'll see, these diagrams are very useful. In addition to telling you about space, the orientation of the wave function, you can analyze a variety of properties about the material. One of the things I didn't include this slide, remember that if the atomic orbital function that you're combining is an antisymmetric function, then the way in which these lines run changes. So if we're making a linear combination of p orbitals that don't change sign, you get an antibonding MO, right? And what that means is that as you go from 0 to pi over a, instead of running up in energy, it will run down in energy. So that chain of platinum cyanides is sort of a nice depiction of that. If you know the orbital basis, you can explain why the various component orbitals run up and run down. So make sure you can understand that problem, okay, that linear chain problem. Now, we went on to talk about graphene. And I'm not going to return to that. So the other way that physicists talk about this helps us understand these diagrams in a slightly different picture. And this is what's called the free electron model. And physicists like to describe electrons as particles in solids, but they have both wave and particle character, and that aspect of quantum mechanics becomes important. The energy of a free electron is a function of its potential energy and kinetic energy. And in a lattice, you've got electrons and nuclei. And nuclei are positively charged, the electrons are negatively charged. And so there's some kind of attraction between the two. Okay, and that gives rise to a potential energy. There's also a kinetic energy that's determined by the velocity of the electron. And you know that that also relates to its wavelength. So you can think about this in classical terms or in quantum mechanical terms. And remember how we talked about this K value, the momentum, quantum mechanical momentum is related to the wavelength as well. Okay, so you're going to hear this. You know, we're not going to get into this in detail really, but at the bottom of one of these E versus K, so here's 0 to pi over A. Near the bottom of this symmetric function, sort of s orbital like functions, this curve looks quadratic. Okay, so the energy dependence of the curve is approximately the square of K. So this approximation is frequently used by physicists. Talk about electron motion in solids. All right, so you can also think about this as it relates to this Frost circle, sort of molecular orbital representation of energy. And a really valuable thing is that at the bottom of the band where K equals 0, this is approximately true. Okay, so here we're looking at the orbital interaction strength, unit cell dimension, and then the mass of the electron and its momentum. Okay, so the orbital interaction strength turns out to be related to something called the mass of the electron. Well, it's not called the mass. It's related to the mass of the electron and Planck's constant. So this is approximately true, but crystals modify this substantially because kinetic energy is also influenced by the attraction to the lattice. And physicists use something called an effective mass in its place, as we'll see in just a little while. And that relates this orbital interaction strength to it sort of gives you a measure of the orbital interaction strength of the lattice, as we'll see. So let's take a look at a number of these. Or first we'll look at one other property. Okay, so when you have two different E versus K diagrams, right, these two have very different bandwidths. And this is the all bonding combination, this is the all anti-bonding combination. And the spread in those guys is related to the strength of the interaction. If they're totally separated, there's no bonding or anti-bonding, and it would just be flat as you change the sign of the orbitals. So that gives rise to a different sort of curvature of these lines. And it turns out if you just take the derivative of this thing with respect to K, then you get this relationship. This is the curvature d squared E dk squared. That is a measure of the curvature of the line, and that relates to this mass. Okay, so when you look at one of these guys here, you can see the orbital interaction strength being different, and that implies that the mass of the electron in those two crystals is different. Of course, the electron only has a single mass. But what we're talking about here is what's called an effective mass, and this gives us a measure of the strength of the interaction between the lattice and the electron. All right, so I'm not going to do a very good job of explaining the origin of this terminology, but what I want you to hear from me and what I want you to take away from this discussion is that people talk about this property, effective mass, as a representation of how freely electrons move in crystals. I think about it in terms of delocalization because I'm interested in quantum dots, but in bulk crystals, it's really just how tightly bound the electron is to the lattice and how freely it moves. And that is influenced by the orbital interaction strength. So if you have strongly interacting orbitals, then the electrons can easily flow from atom to atom in the crystal. And you can measure orbital interaction strength by looking at the curvature of an energy versus momentum diagram. This one is not curved, this one is highly curved, and that tells you the orbital interaction is strong and the effective mass of the electrons is low. So here's a handful of different semiconductors. We have group 4 semiconductors, so carbon, germanium, silicon. We also have what are called 3-5 semiconductors, 2-6, and then 4-6. These are sort of classic binary materials that have been studied in tremendous amounts of detail. They're relatively simple solids. Most of them either have a, they all sort of have the diamond structure, but there's two atoms sort of alternating throughout the crystal. Turns out there are two different arrangements. There's either the all staggered arrangement, or there's one crystal structure that has staggered 2 directions and eclipsed in the 3rd direction, but approximately like a diamond structure. So they're very similar. The exception is the 4-6. These guys are rock salt crystals. In any case, these are relatively simple solids and have been studied in great detail. Now, what I've shown here is the effective mass divided by the real mass of the electron. Okay. So this tells you to what extent would you say, or how much is this electron like the free electron versus how tightly is it bound to the lattice. So the magnitude of this number, you can think about numbers that are very high as having a heavy mass, and numbers that are very low as having a very light effective mass. So there are a number of trends that come from this, but let's just stop and remind ourselves the way we're going to think about this binding. It's related to the orbital interaction strength. Okay, so it's sort of a measure of the bonding in the crystal. It also, it turns out, is related to the ionization energy of the atoms in the crystal. So how positively charged are they? How attracted is that electron to the atom in the lattice? So let's look at there's also two different graphs here. We're looking at holes and we're looking at electrons. So holes really are electrons that sit in the valence band. So these are charges that sit in the valence band and charges that sit in the conduction band. And you'll notice the numbers on the right are quite a bit lower than the numbers on the left. Okay, so why is that? Guess as to why that would be. This relates to the orbital interaction strength that we've been talking about, or the bandwidth. Okay, so remember, this is a description of the valence band. It's written as holes, but it's a description of the valence band. This is a description of the conduction band. That's because if you push the Fermi energy or you dope in a semiconductor, you fill up the electrons, you fill up the conduction band with electrons. If you pull electrons out of a crystal, you deplete the valence band. Okay, so this is described as being valence band holes, and this is described as conduction band electrons. Why would the electrons that sit in the conduction band have a lower effective mass than those in the valence band? This relates to the bandwidth that we've been talking about. Remember that in most of these materials, the conduction band is going to be made up of s orbitals. The valence band is going to be made up of p orbitals. And s orbitals make stronger bonds than p orbitals do. And so conduction bands tend to have broader bandwidths, and therefore they have lower effective masses. Stronger orbital interaction means lower effective mass. So electrons tend to move much more easily in conduction bands than they do in valence bands for these kinds of materials. Another thing that you can glean from this diagram is that as you go down, the column, so let's take a look at the conduction band electrons for these 3,5 semiconductors as you go from aluminum to gallium and then down toward indium. You can see the numbers dropping. Okay? And that makes sense when you consider the electronegativity of the atom or the ionization energy of that atom. Right? As you go down the main group, the electrons get further from the nucleus. The nuclear charges don't interact as strongly with those electrons, and they're more easily ionized. So the result is that the electron is much lighter as you go to larger radius elements. Okay, so another interesting thing another aspect of this effective mass is that it's related to the charge transport mobility. So charge transport mobility is an intrinsic measure of how easily an electron moves in a crystal. Okay, it's sort of like a conductivity, but it's per electron. So this charge transport mobility is an intrinsic measure of the property of the solid, and it's 1 over this effective mass. So when you look at an energy versus K diagram and you see the curvature of the lines on that diagram, if you look at that, you find a band that has a very high curvature, that tells you that the effective mass of the electrons in that orbital is going to have a high charge transport mobility. This is a pretty interesting idea, I think. You can look at one of these molecular orbital diagrams and estimate how easily electrons will flow. And it sort of makes sense, as I was saying, the orbital interaction strength of the atoms in the crystal impacts the degree to which the electron can be in multiple places at one time, and it reduces that binding to the lattice, and that makes the electron flow better. So more delocalization, in molecular terms, tends to give rise to higher charge transport mobility. So a classic example of this is the E versus K diagram of graphene. You remember we talked about this K point where the two energy versus K lines cross. That they cross right at the Fermi energy in graphene or in graphite. So you have the pi and the pi star orbital basis crossing. This is the K point in that Whirlwind diagram we were looking at before. And if you think about this point right here, these two lines, because they're approximately straight at that position, where they cross, the curvature I'm going from this line to that line is basically infinite. So the curvature is very, very high, exactly at that point. And so people say, all right, well, the curvature is high. That means that directly, if the Fermi energy is exactly at that point, the so-called Dirac point, the electrons in graphite or graphene have zero effective mass. They're not bound to the lattice at all, and their charge transport mobility goes to infinity. So this is why graphene and graphite are very, very good conductors of electricity. You know, you can make single sheets of carbon atoms that transport charge with extremely high mass. Okay, so this is one of the really valuable things to remember about these diagrams when thinking about solids. Okay, so effective mass also impacts optical properties, and we're going to kind of work up to this because it's relevant to political quantum dots and their size-dependent optical spectra. So, unfortunately, I think I might be out of time. I have a few more minutes. Sorry, I feel like we just got started. Yeah, I have about 5 minutes left. So we're going to go ahead and launch into this to kind of get off the ground. You're familiar with visible absorption or light absorption in a molecule. So you might have a HOMO-LUMO transition or a charge transport transition. And this is a resonant transition between two energy levels, generally speaking. Not that simple, but you know, you think about a single optical absorption process. And that tends to have a band of a particular energy that's equal to the spacing of the two MOs in the diagram. In a semiconductor, you have a very different situation. So you have a whole band of filled states and a band of empty states. Any photon that is wider than the band gap can in principle promote an electron across that gap. And so when you look at the absorption spectrum, you get something called an absorption onset, where the probability of the transition is high. You know, in some materials, that's going to be the top of the valence band and the bottom of the conduction band. And then if you go to higher energies, there are many more levels down here, and there are many more acceptor levels up there to which you can promote. So the further you get from the band edges, the more transitions become viable, and the absorptivity of the semiconductor increases. So you get this kind of threshold behavior, and then the curve grows in intensity. Absorbance increases in intensity as you go to higher and higher energies. Semiconductors have gaps between about 0.1 and 3 electron volts. Okay, so that's a pretty wide range of energies. 0.1, you're talking about 12,000 nanometers. So you're out in the far infrared here. You know, way beyond where you measure an FTIR spectrum generally. 3 eV is right at the edge of the visible, okay, right around ultraviolet wavelength. So pretty wide range of that gap. Each one of those materials will have a different onset in energy space. I always like to sort of put these up here. Remember, 1 electron volt is 1240 nanometers, 8,000 wave numbers. Depending upon whether you're watching a physicist or a chemist talk, it's different units. When you absorb a semiconductor, you promote a charge, and then very rapidly, both of those charges tend to relax down to the band edges. The jumps in energy between the various orbitals within the band are very small. And so lattice motions are enough to accept the energy of those electronic transitions. And so the crystal basically heats up in a few picoseconds. Those charges, the electron falls down and the hole bubbles up. Right, so I talked about holes earlier. This is a hole produced in the valence band. You can talk about the electrons falling down to fill that hole, but generally people think about the hole moving instead. It's equivalent. So the hole bubbles up, the electron falls down, and now those two charges sit right at the edges of the gap. And if you have a good material, it will produce a reasonable amount of light. Not all materials are luminescent, but you'll see this luminescence band, and typically it sits right at the band edges and tells you about the band gap energy. So you can estimate the band gap energy in crystal by, at least at first glance, by looking at absorption onset and the emission. So things get a little more complicated when you begin to consider, and more interesting when you begin to consider the energy versus K diagram. So here's a simplified energy versus K diagram for gallium arsenide. We're looking at the valence band here. This would be 0 to pi over A. The conduction band, 0 to pi over A. And it turns out this is about the Fermi energy, or here maybe. And the band gap is defined by the bottom of that curve, the top of that curve. Now, why does it look like this? It looks like this and this. These two have opposite sign on top and on bottom, right? One of them, as you go from 0 to pi over A, is running up, and the other one is running down. That's a consequence of the fact that the valence band is made up of sigma bonding orbitals composed of arsenic 5p levels. These are p orbital sigma bonds. Up here, the conduction band is primarily composed of gallium s orbitals. Okay, so we have s at the top, p at the bottom. That's why those two have different signs, right? Because those component functions run up and run down. The result is that the band gap energy, you see the bottom of this band and the top of this band, and they share the same value of momentum. This is not always true. Okay. But because that's the case, gallium arsenide is said to be called it's a direct band gap semiconductor. And transitions, optical transitions that share the same value of momentum, when the electron is staying at k equals 0 and going to k equals 0, those are symmetry allowed transitions. Okay, so people talk about, is it direct or indirect? What they mean is, are the optical transitions at the band edge symmetry allowed or symmetry forbidden? Gallium arsenide, because it has this structure where the top of the valence band and the bottom of the conduction band are at the same value of k, have optically allowed transitions. So gallium arsenide is a luminescent material. The electron, when it falls to the bottom of the conduction band now, the transition back to the top of the valence band is symmetry allowed. So it's highly probable gallium arsenide is luminescent. Let's do one more. Here's silicon. Silicon's conduction band looks a little different. Or hybridization, maybe. The P and the S levels are more similar in energy. And so you get this wonky looking E versus K line for the conduction band. Okay, so now the band gap is the lowest energy conduction band level and the highest energy valence band level, but they are not at the same value of K. So that means that when the electron cools to the conduction band edge, it has a different momentum than the valence band edge. And the transition to go from the conduction band to the valence band is improbable because it has to change momentum. Okay? And so because they don't share that same momentum, silicon is not luminescent, or it is very, very, very weakly luminescent. This is one of the reasons people like it as a photovoltaic. Because when you excite a crystal of silicon, the excited charge and the hole don't really want to recombine with each other. It's a momentum problem. So they tend to have very long lifetimes. If you look at the diagram, the absorption spectrum for silicon, you get this very interesting behavior where there's an absorption onset that's way out here at the band gap energy, but it's very weak absorbance. Silicon does not absorb very well at its band gap. But if you go to higher energies, eventually you get to regions where there are vertical transitions on this E versus K diagram, and those are strongly allowed. So if you look at the transition from this orbital here at the top of the valence band to the orbital that also has K equals 0, there are allowed transitions at that energy, and they fall in this region out here. So suddenly the spectrum becomes very intense when you finally reach energies where the optical transitions maintain the momentum. Okay. So quite a bit of the spectrum of silicon is very, very weak. It's not a strong absorber. It's not a strong emitter because that band gap transition is improbable because the two states have different momentum. All right. Turns out one of the things you can do to improve the probability of this is to add a phonon to the mix. So you can actually do it. If you add phonons to the mix, you can change the momentum of the electron. And the combination of a photon and a phonon allows this transition to happen. So you can change the electron energy by adding a phonon to it. And what that means is that the luminescence of silicon can actually become brighter as you heat the sample. All right. Let's see. Yeah, so radiative recombination in this material system is more like microseconds to milliseconds. That's really slow. Radiative recombination of gallium arsenide is going to be more like nanoseconds. So I think in the interest of time, I'm going to stop with that and I'll come back to this stuff. I'm sorry to have gotten started late to have to end early, but I got to go give a talk. That was kind of out of my control. So I will see you next week. I will aim to get your review comments back to you before then. I have a ton of stuff to do by Monday. So I have a problem. Okay. Yeah, thanks, guys.